Greetings and salutations. My name is Andrew Austin, and today I'm presenting, alongside my fellow classmates, Newton's universal gravitation constant, alongside Trinity herself, Paul Neely and Jeremiah Tucker. All right.
Alright. So for our introduction, we see this graphic right here. And this represents like the iconic apple falling from the tree. Or it's more legend. I don't think there's any documentation of it happening, but per legend, Newton sits beneath the tree, apple smacks him in the head. He starts thinking about gravity and studying it. So the basics here we have listed. Double one mass doubles the force. It weakens at a distance. Okay.
Ready.
Gravity acts along the line between masses and is always attractive. Like as in the Earth, physically pulling things towards it.
Okay, on this slide we have universal gravitational constant and the relevant formulas that apply. So our core formula is force E equals big G times mass 1 times mass 2 divided by radius squared. Essentially what that means is that there's two center points in any mass and they're attracted to each other, and then in order to get the formula you multiply the masses and divide them by the radius squared, and that will give you the gravitational constant or the force. So also we have the formula that can be used for a lot of different sciences or laws. So one of them is the tidal effects and the orbital patterns. Basically how the Earth spins through the tidal waves is, it's not like you would normally think. The Earth is spinning while the mass of the moon is pulling on the Earth, causing the tides to come outwards. So basically when we're spinning we're spinning into a tide. So the tide's not really actually rising, it was already at its height, it's just that we're rotating into it. So that's why tides go up and down. Now, as far as the universal gravitation is an inverse square law, what that basically means is that the attraction between two objects decreases proportional to the square of the distance between them. So basically, as the numerator grows, then the distance or the attraction will lessen.
The universal gravitational constant is useful in many areas of work, design, and expertise. Some fields are related are astronautics and aeronautics, and some fields you wouldn't even think of are coastal engineering and navigation design, where you would design seawalls to protect coast from the tides, or to make corrections in GPS systems to improve accuracy.
Hi, I did my slide on relevant sciences and I chose Henry Cavendish. Henry Cavendish was a wealthy aristocratic. Okay, start. I did my slide on relevant sciences. I did my slide pertaining to Henry Cavendish. He is a wealthy scientific man. He loves science so much, and he is best known for the Cavendish experiment. He used the Cavendish experiment to find Earth's density, but in order to find Earth's density, he has to find gravitational constant. He converted most of his home into a laboratory, so he used the small space. He selected a small space while everything else was science. He conducted many chemistry experiments and physics experiments. Newton's law says every particle attracts every other with force proportional to their masses. Newton published the law without knowing Earth's mass. However, Cavendish found Earth's density and everything else was history. I'm good. The original Cavendish experiment was used on a torsion balance. A rod with two spheres attracted one larger place nearby. And how it works, the gravity caused the spheres to attract each other. This made the rod twist slightly, and the wire created, restoring the force, making it move like a horizontal pendulum. And that is our formula: force equal gravitational constant times mass and times the second mass divided by the radius squared. And the data collected, Cavendish placed the experiment in a sealed room. He observed the movement using a telescope, and this helped him measure very small changes accurately.
Alright, so here we're going to look at some of the difficulties. An important caveat you have to remember here is that this is all being researched in the 18th century, and there's quite a few leaps in technology and research since then, but given what these men had access to, it's still pretty remarkable what they achieved. So I'm just kind of go over the basics. So it assumes that attraction is instantaneous. You remember, they have very primitive measurement devices. They only do so much. So to make it easier on themselves, they have to make that assumption. The inertial mass is measured in resistance, also sets gravitational strength. Newton's model also depends on inertial masses of just what he was studying at the time. And looking at the universe in its entirety, that's beyond the scope of what he could even look at. Though it did prove a great starting point for scientists after him and all the way up to today's research.
To present the experiment motivation, the motivation for Newton's law of gravitation. The motivation for the actions that took place in discovering the universal gravitational constant just started with Isaac Newton asking questions about a concept now referred to as gravity. Eventually, the experiment that found the constant itself was conducted by a man named Henry Cavendish, and it was formerly known as the weighing the Earth experiment.
Okay, so on this slide, it's about universal gravitational constant and the original benefits. Newton unified terrestrial mechanics, which is the motion of the Earth, alongside with the celestial mechanics, which is basically the motion of the planet and stars. His law helped strengthen faith in natural law, kind of got away from the old thinking of the churches and more into the actual world of science. The objective thinking, objective questioning about the reality around you. His work helped to replace the geocentric view with world mechanics. So back in that time period, they used to think that Earth was the center of the universe. And this was based on the divine laws, rule of the monarchy, such as that. So through his science and through his law, basically explaining that the Earth is going around the sun alongside with other planets instead of being the center of everything. So John Locke, one of the Enlightenment figures, along with Voltaire and Isaac Newton, they used Newton's ideas to help form the Enlightenment period and used that to shape politics, which eventually came to more natural rights theories that then spawned later on into the early writings of the Constitution, and also came from prior Enlightenment period thinking like the Magna Carta, all involving the Enlightenment movement. So Newton's work had a big profound effect on shaping Enlightenment thinking towards getting away from the ideas of the church and what was mandated by their faith versus bringing it into a new age of science and being able to test and quantify and theorize everything.
In the for the modern Cavendish experiment process, it uses two dumbbells. One dumbbell hangs from a thin quartz fiber so it can twist, and the other dumbbell is moved to bring bigger spheres closer to the small ones. How it works is when the spheres get close, gravity pulls them, causing a twist. The twist is super tiny, so it can be easily measured. So they use a mirror and a laser to try to track the movement with light. And how the data is collected, the scientists look back at how the fiber moves back and forth. This helps to find something called the torsion constant. When the big spheres are moved to the other side, the twist reverses in a different direction. Both movements are recorded for accuracy. And by looking at the twist in the movement, they calculate the gravitational force, and this is then how you find oh my god, I'm gonna have to do it. And how they find the gravitational constant.
On a previous slide, we discussed the primitive nature of Newton and Cavendish's experiments and how that kind of can be problematic in the modern studies. However, in this slide, we address how we've overcome that. Quantum theory condenses it to very tiny particles. Yeah, because now we know about things like atoms, molecules, and whatnot. A very, very useful knowledge that Newton and Cavendish did not have. And by combining this modern knowledge with the old ideas, we can now study the subject further and make new discoveries, or at least at minimum, make the old discoveries make more sense.
The modern day benefits of the universal gravitational constant gives life to humanity's curiosity to find out what is beyond the Earth's atmosphere. Without it, space travel would be impossible, and other benefits of the universal gravitational constant enable high-end navigation and communication technology, making life easier and more convenient.
Go.
And lastly, for our group presentation, is going to be this last slide, talking about the future expectations. So, MIT researchers are working to determine if gravity can be quantized. They are developing new sensory tools that are very precise in measuring gravity. And most of the issue with measuring gravity is that there's a lot of interference because gravity is such a weak force that other forces, just a vibration from outside, can interact and cause the measurements to come back with the wrong information. So what they're doing now at MIT, they have researchers that are using laser-cooled torsional oscillators to focus light beams on a detector. And when one laser may have a slight vibration that picks up, the other laser basically is the fail-safe that will cancel out any of the other noises or effects that can override their measurements, giving them precise measurements. This approach that they have and working on reduces the noise factor by about a factor of 10,000 and allows them to detect with extreme precision so that they can basically finally ask the question, can gravity be quantized or observed in the quantum field? Because right now gravity is only a part of the macro forces, which are like the weak nuclear forces, and then the gravity, weak nuclear forces, and then I'm missing one. Pause.
Go.
Basically what that boils down to is that they're trying to see if gravity can be measured in the quantum realm. As far as we know now, we have the macro forces, which are the strong and weak nuclear forces, electromagnetic force, and